Welcome to Calibration Optimization Process Descriptions, and thank you for your interest. We hope you'll take time after this short presentation to explore the other Triad Unlimited presentations on YouTube, follow us on LinkedIn, and visit our website to see all our service and training offerings. Calibration Optimization serves to develop calibration specifications, calibration intervals, advanced analytics, and verification guidelines. Calibration optimization is about executing and improving calibration by creating rules for calibration accuracy, intervals, proactive performance diagnosis, and defining the circumstances that require calibration outside of normal intervals. There are 4 processes associated with calibration optimization. First, calibration specifications have to be defined and developed. Then, calibration interval decisions have to be made. Then, we figure out the calibration advanced analytics, how we're going to diagnose impending instrument problems. And finally, calibration verification, where we set up guidelines to verify when calibration is required outside of set intervals. Calibration optimization has several benefits. Loop calibrations are more efficient than individual calibrations. Calibration interval optimization ensures calibration quality goals can be met. Calibration analytics provide means of continuous improvement of calibration processes. And optimized calibration specifications better support the overall manufacturing process and product regulatory requirements. Calibration specifications provide a process for the way an organization approaches calibration execution by defining rules for the information necessary to perform calibration. Common information found in a calibration specification includes instructions on how to perform the calibration, how often the calibration is performed, values that are going to be tested, the acceptance tolerance for the calibration, as-found documentation and as-left documentation, and the pass-fail indications for the calibration. All of these things can be included in a calibration specification, both for the benefit of the technician who's performing the calibration as well as the personnel who may eventually audit, investigate, or otherwise need information about an instrument or calibration performance. They need to interact to create the parameters of the associated calibration specification. So basically, when developing calibration specifications, as much information as is necessary to permit a qualified individual to perform or to audit calibration needs to be included. It's certainly a best practice to have the calibration procedures conform with a single format for ease of use and consistent data collection. Other things to be considered are whether calibrations will be performed as a loop or individually or in the field or on the bench. These considerations will all be addressed in more detail in function process training later. Calibration interval decisions establishes a means to assign calibration intervals to instrumentation. The idea here is to achieve optimal calibration intervals. Optimal means not too often and not too infrequently, but enough to stay in calibration for the duration between intervals. And that is just about where real direction on the matter ends. As shown in the slide, there are books written on the subject, and I am not about to go into detail on the various methods and advantages and disadvantages of each. That is a topic for another day. I am going to say that manufacturers' recommendations are a great place to start in absence of any other directions. That said, there are many influences on how long an instrument can be expected to remain in tolerance or calibrated that the OEM recommendations might not consider. These influences include things like the operating environment, such as hot or cold ambient temperature. Past shocks during transport or improper storage environments could influence the instrument's resistance to deterioration and hence the length of time it remains calibrated. Regardless, our certainty about the accuracy of an instrument begins to diminish as soon as a calibration is completed, and however long we can tolerate that uncertainty is the interval that we want to establish. So the short version is that intervals can be established by using complicated statistical models or by review of pooled or published data about the same or similar instruments, or by starting with OEM recommendations. The decision about intervals should be made by a person or by persons with general experience of measurements or of the instruments to be calibrated, and preferably who also have knowledge of the intervals used by other laboratories or facilities. An estimate should be made for each instrument or group of instruments as to the length of time the instrument is likely to remain within tolerance after calibration. Calibration advanced analytics methodology is the process used to improve overall instrument performance. At present, in common practice, advanced analytics can mean many different things, and that doesn't matter. The bottom line is that one of the functions of a calibration program in a risk-based asset management program is improvement of instrument reliability. So from counting deviations to developing machine learning algorithms to predict instrument performance trends, the method is not as important as simply having a method, utilizing it, and tracking improvement. The process just has to be defined in terms of data requirements, interfaces with other reliability processes, roles and responsibilities, and reportability so it is auditable and sustainable. Periodic trending reports should be created to identify poor-performing calibrated instruments. Annual review of periodic trending reports should be executed to determine if any poor performers should have a reduction in calibration interval or be replaced. Calibration verification creates guidelines for verifying instrument calibration outside of set intervals. Calibration intervals are great, but there are other events that require a calibration to be performed. The calibration program must identify those events or circumstances and make provision for how they are triggered and how they interface with the regular calibration tracking and information processes. The usual reasons to perform calibration, other than when scheduled, include changes to operating configuration or parameters to ensure that the instrument calibration specifications remain valid in the new operation. Troubleshooting or verification of questionable instrument performance. This can be triggered by direct indication or alarms that are spurious or inappropriate for the operating context, or observation of damage or other motivation to determine if an instrument is operable. Installation of new instrumentation. When instruments are stored in an unsuitable environment or they are mishandled during transport. When the calibration period is exceeded. Process requirements when some operations will not be executed unless the equipment has passed the calibration and verification process. This can be applied during commissioning and validation, or when a process is so critical or valuable that calibration has to be performed immediately before operation. And finally, audit requirements, such as for certification for ISO. Here's the calibration optimization summary. Calibration specifications must contain adequate information to be executed and audited successfully. Original equipment manufacturer recommendations are a good place to start when developing calibration intervals, but they may not consider local operating environment. Advanced analytics drive continuous improvement, and the calibration program must define triggers for calibrations performed outside of normal intervals. This concludes the Calibration Optimization Process Descriptions presentation. Thank you for your participation.